Okay, my background is mostly in AI ML. I've worked at Amazon, I've worked at IBM, I've published some research papers, and yeah, that's pretty much all you need to know about that. So today we're going to cover. Oh, by the way, you guys, everyone wants to see a code example, right? Raise your hand if you want to see a code example. Okay, great. Okay, so I'm going to run through this part really quickly. I'm going to just run through this. This is some concepts. We're going to go through basically a primer on large language models, and then we're going to go through how you can use vector databases for language models, and then we're going to go through a multi-document querying architecture. So this is a architecture for a type of retrieval augmented generation application that's very, very popular among enterprises, and it is because enterprises have multiple documents. Then I'll cover some FAQ. Okay, so we're going to start. We're going to start with this. Has everybody here taken an introduction to machine learning? Not a lot of people. Okay, so I'll explain neural networks then. Neural networks are basically your building block for machine learning, right? What they do is they take some sort of input and then they run it through a bunch of calculations and they make a nonlinear. It's a nonlinear function, and then it produces some sort of prediction. So what are the advantages of this over something like, I don't know, like a decision tree or like flipping a coin or like Bayesian statistics? Essentially, because you have many, many layers and you have many, many nodes and many, many connections, you can create a high dimensional representation of your data, which allows you to abstract out many features that you otherwise would not be able to. Okay, this is a very basic neural network. Nothing's built like this anymore. If you can build a neural network like this that performs well, you're like a savant. Okay, after we built neural networks, we were like, this is mostly about large language model. I'm sorry, this is mostly about language. So there's recurrent neural networks were invented basically to deal with text, to deal with a sequence problem, right? So what recurrent neural networks allow you to do is they allow you to keep track of how your tokens have come in through a time model. And it essentially kind of helps solve the sequence-to-sequence problem. But recurrent neural networks have a problem with the sequence-to-sequence problem, and that is that they can only do sequences of the same size. So what do we do to answer that is we created the transformer architecture. So the transformer architecture, you basically start with an input, and then you give it into an encoder, and this encoder produces some sort of state. This hidden state is basically a matrix. You see the word hidden state, just think bunch of vectors or matrix, okay? And then additional input, this is typically self-attention or some sort of attention mechanism. This is also just a matrix. So what you're looking at here is some sort of input data, some sort of black box, matrix, another black box, and output. So the advantage of this is this solves the sentence transduction problem or sequence transduction problem. Essentially, you no longer have to care about your sequence size. It will give you something that makes sense regardless of sequence size. And this is the most recent, most famous kind of thing that has been going on with neural networks. GPT is your, classic, or I guess not classic, but most popular large language model, and it is a decoder-only model. And so this is very different from former implementations of neural networks because it is only decoders, which the transformer neural network is an encoder decoder. And so if you know about BERT, if you've heard BERT, who's heard of BERT? That's an encoder only model. So BERT produces a matrix, a hidden state. Basically a hidden state. GPT takes in some sort of state. So it takes your data and it converts it into some sort of state. And then it decodes all of it and it produces out the output. So what makes this different is that essentially what it's doing is it's predicting the next token. Okay, it's not actually predicting the next word. It's kind of predicting the next word, but it's actually predicting the next token. Okay, so it changes. It's a different problem formulation. You're not classifying anything. You're not trying to predict is this a word or is this a question mark? Okay, so how can you use vector databases with large language models? Essentially, when you're building your retrieval augmented generation, you're going to be looking at this kind of stack, right? So you're going to need some sort of LLM. We've decided to call this stack the CVP stack. I think there can be better names, but this is what we've decided to call it as a company. So ChatGPT or any other LLM is your C. This is your compute power. This is your processor. Whenever you're building an application, you have something that runs most of the compute, that does most of the processing, right? This is what that is. This is essentially your compute. So if you think of this as a computer, this is your CPU. Then you've got a vector database such as Milvus, and this is your storage, right? If you think about this as a computer, this is your hard drive. And then you have the prompt is code, which is some sort of mechanism to essentially put these two things together, your storage and your compute. And how do you interface with it? So that's the prompt is code. Some examples of something you can use for that are Haystack, LangChain, and Llama Index. And later on, I'm going to show you an example of using Llama Index. So how does RAG work? You take your knowledge base, your personal documents, right? So the problem with large language models is they do not have access to your data. And this is problematic if you're an enterprise because you don't care about public data. You care about what's going on inside, right? So you take that knowledge base, you run it through a deep learning neural network. This is typically called an embeddings model, but it's really just a neural network that's trained on the data that you want to work with, or trained on the type of data that you want to work with. For example, if you were working with text data, you want a network that was trained on text. And if you're working with images, you want a network that was trained on images. And then the embeddings model will produce a set of vector embeddings, okay? These vector embeddings are actually produced from the second to last layer. So what actually happens with these models is we cut off this last layer here. This is your prediction neuron. And we just cut this off, and the output is some vectors. Then you store those vectors into some sort of vector database like Milvus. And then when you need it, you can query against those vectors with another vector that is also produced from the same embeddings model. Okay, so let's cover how similarity search works. This is a diagram that shows you how semantic similarity works, right? So as I was saying earlier, you start with some sort of data. And in this case, we're starting with any set of unstructured data. You can think about this as your knowledge base. And we're putting it we're creating vectors and vector embeddings, and we're doing this through a neural network. Then we're putting it into a vector database. And this is all you need to do to store your data. Here, we're cutting this off, and now we're doing the second part. Part two is querying. So you come in, you have your knowledge base, your unstructured data, you do the same thing. Same model, you get some vectors, and then you query the vector database, and it will give you back your approximate nearest neighbors inside of the vector database. This means it'll give you back the closest, most semantically similar vectors. Most semantically similar data, the most mathematically close vectors. I'm going to walk through a really quick example of how semantic similarity works so that everybody understands. Okay, so we're going to look at here. We're going to look at 4 words. So I want to emphasize that this is a toy example. Okay, you will never see 2-dimensional vectors in production. If you do, you should run. But basically, you can see that queen and woman are very similar on the first axis. They have the same value. Same with king and man. So this means that these words are very semantically similar, or even semantically the same along one axis. Now, the second axis, you can see that these words differ by a little bit, and these words differ by a little bit, and they differ by the same amount. What this means is that these two words and these two words have the same relation along the second axis. So what I want you to get out of the next few slides is basically that vectors allow you to do math on things that are not numbers by turning them into numbers. Okay, so what's going on here? We have queen, king, woman, and man. And I want to show you that queen minus woman plus man is equal to king. So queen is 0.3 comma 0.9. Woman is 0.3 comma 0.4. You subtract these, you get 0.0 comma 0.5. So this probably means something like royalty. Okay, so you add the word man. Man is 0.5 comma 0.2. And what do you get? You get 0.5 comma 0.7, which just so happens to be king, right? So once again, all you really need to get from these slides is that vectors allow you to do math on things that are not numbers originally. I also want to point, you're never going to see anyone use Manhattan distance like this in real life. And once again, if you do, run. This is what a vector database looks like. This is specifically a Milvus architecture. And so, there's most of this you don't need to pay attention to. I will call out Pulsar here. Pulsar is a streaming thing, is a open source streaming platform that Tim has worked on. So what you really need to know here is this set right here. There's a query node, there's a data node, there's an index node. And the reason why this is important is because these three things are the three separation of concerns for any search type of application or program or software or whatever. You're gonna find some way to index your data, and then you're gonna find some way to put data into your database, and then you're gonna find some way to query it. And so these things are all done separately. And so we've created a way to scale them up separately. And this is one of the features of Milvus that's unique. If you go look at other vector databases, they're not built like this. And we've did this because Milvus's niche in the vector database world is enterprise scale. Milvus's niche is specifically that we scale to billion plus vectors, okay? And then the last thing is the query node and, the next thing is the query node. And this allows you to do the queries. And so if you have high throughput, you wanna scale this up. Like if you have high TPS, you wanna scale this up, right? The other thing that's really interesting about Milvus is that we create data and store data in these things called chunks or segments. Segments. Chunking is what you use for text. And what that essentially means is, as you scale, what we're going to do is we're going to search smaller data chunks in parallel rather than one large data chunk in series. So let's just do a quick thought experiment here. If you have 100 gigabytes of data, do you think it's faster to search 200, 512 megabyte segments and coalesce the data at the end, or search the entire thing in parallel? Right, we want to query the segments, which is exactly what we did as the architecture, and that's why Milvus scales so well. Okay, so now I'm going to go over a quick architecture diagram. This is what a multi-document query architecture diagram looks like. So I'm going to walk through this once, and then I'm going to walk through it again later in the code, okay? So step one is you have your query. You have some sort of question. What happens is you send this to some sort of query decomposition engine. What a query decomposer does is it breaks your query down into multiple questions. For example, if you have the question, tell me about the differences and similarities between the Seattle and New York airports. What it would do is break that down into, tell me about Seattle airports, tell me about New York airports. What are the names? How big are they? How many terminals do they have? Et cetera, et cetera, et cetera. That does that by calling the LLM. The LLM is what does the query decomposition, okay? So that's use number one for your large language model. Once you have your query decomposed, you send it to some sort of splitter. And in this case, I've used a keyword index. You can also use like a graph index or something else for this if you would like, but this is what we're gonna do in this example. So let's say we're asking about Seattle and New York, right? So essentially what will happen is it'll go through the keywords and it'll say, give me the keywords that correspond to Seattle. And once it does that, it says, okay, now give me the vector index that corresponds to Seattle. So for each of these keywords links to an entirely separate vector index. Now they are all contained in the same database, but that does not mean that they are all each accessible just randomly. You have to access them through the keyword index, okay? Once you get that back, we send it back to the LLM, and then that formulates that response into a human readable response, and that gets sent to you, okay? So this is what we're gonna cover in code in a second. If this was complicated, don't worry. I had to do this like 10 or 12 times before it made any sense to me. So here is a QR code that, if you have your phone, you should probably scan this. This will lead you to the Colab notebook that allows you to, the Colab notebook that I have that does this multi-document querying thing, okay? So before I'm gonna just keep this up. It seems like people's phones are still up, so keep this up there for a little bit, and then I'm gonna go over a quick FAQ section, and then we're gonna dive into the code. I have two code examples for you. One is just a primer that tells you like how does Llama Index work, and then the second one is about the multi-document querying. So some FAQs people often ask is, when should you not use a vector database? I think that if you talk to anyone who like presents about their technology and they can't answer this question, they don't know what they're talking about. So when should you not use a vector database? You shouldn't use a vector database if you are building something that only does key value stores. For example, if you are trying to create a user base, you want a direct match, an exact match each time for your users and your passwords. You don't want an approximate match. You don't want similarity search. You don't want comparisons. That's what vector databases are for. So if you're building something that is only key value stores, use SQL or NoSQL. Okay, a lot of questions. I get a lot of questions about CSV files, PDFs, right? These are both technically text, but they are encoded differently, and you need to have models that are trained on that type of text in order to get the correct embeddings, or else your embeddings won't be good. The last thing I get asked about is hybrid search. Hybrid search is, how do I do keyword search and vector search, and is it possible? The answer is yes. Milvus stores metadata. Just throw your text in there as metadata and say, hey, I want vector search, but I only want it if these keywords are in the metadata. And that's pretty much it. That's pretty much all there is to this. So I'm going to go back to this architecture diagram, and then I'm going to go to the code. All right, so let's look at this code first. Is this on the screen? Yeah, okay, cool. These are just you guys actually don't have to pay attention to this. I just want to kind of show you some of the functions that we're going to be using, and then I'm going to do it again so that you have, but I want you to have some familiarity when I go through the multi-document one, because the multi-document one is pretty confusing. So essentially what we're going to do is we're going to get a vector store index, which is how Llama index is able to kind of create and interact with your vector store, which in this case is going to be Milvus. And then a storage context. This is how we pass in the Milvus instance that we're going to use. This gives you the context for the storage that Llama index is going to touch. Then we have a simple directory reader. This is just a way to read in a directory. And then obviously we have the Milvus vector store. This is a Milvus. You can load Milvus right into your notebook. You can't do it on Colab right now. It's broken on Colab. I'm sorry about that, but we're working on fixing it. Just do it locally for now. You can load it into your notebook. And this is mostly for environment variables. If you have your OpenAI API token, which I do. Basically, you load in your environment variable token, then you start your Milvus server, then you connect to Milvus, and then you get your documents, you load them up using the simple directory loader, and then you get a storage context. So this part is important. Pay attention to this because we do this again later. Okay, this happens in the multi-document one. So pay attention to this. Essentially, what we're doing here is we're giving it a vector store as a storage context, and then we're giving this storage context to the index. Oh, can I zoom in? Yeah, I can. Better? Okay. Okay, yeah, sorry about that. I forgot. This text is like tiny. You probably can't see it from the back at all. So yeah, this is how we pass in that storage context, okay? And then what we're going to do is we're going to use the index as a query engine. So essentially what this allows us to do is to query the index. And once we have the query engine, we just simply query, what did the author do growing up? And we get some sort of response. Now, this specific example uses, I believe this is Paul Graham's essay. And so this is about Paul Graham. He wrote short stories, programmed on IBM 1401, and nagged his father to buy him a TRS microcomputer. And then at the end, you stop your server and you clean it up. Okay, so now we're going to go into the complicated code. This part, I'm not going to explain this. This doesn't matter. This doesn't matter. This matters. Okay. So once again, we're going to use this vector store index. We're going to use the keyword index. Remember, I showed you earlier. There's the green bar. This is the keyword index. And then there's going to be the directory reader, the LLM predictor. This is what we use to decompose the query. The service context, this is what we use to pass the LLM to the indexes, and the storage context, which is what we use to pass the Milvus to the indexes. I've decided to use LangChain in this particular example as well. You don't actually have to use LangChain. You can actually use Llama Index or OpenAI to do this. But I thought it was funny that we could have an app built on like Llama Index, LangChain, and Milvus, and we call it like an LLM app. So that's why it's in here. Let's see. Here's getting your OpenAI key. Unimportant, unimportant. Starting the default server, unimportant. Connecting to the default server, not unimportant. Okay. We already did all this, so this should be, familiar. Now this is going to be new stuff. So what we do is we're going to add in the wikis, do I have New York in here? I don't know what New York's Wikipedia title is, but essentially we're going to create a list of cities that we're going to query in our example. And then once we create those lists of cities, we're going to go through and we're going to ping Wikipedia's API, and I'm going to scrape all these cities. So this has nothing to do with the RAG app yet. I'm just getting the data, okay? So if this doesn't make sense, if this looks confusing, don't worry about it. So this next part, this is to do with the RAG app. Okay, so we're about to build 4 dictionaries. This is going to be the first of them. The first dictionary we're building is we're creating a dictionary that links the title of the Wikipedia article or the city name to the documents that are related to it. Okay, so this basically says, okay, Seattle documents, let's put them together. Okay, that's what this is. Next, we're going to create some content. Next, we're going to create some context. So what this does is essentially, we're calling the LLM, we're getting our LLM, we're going to be able to talk to OpenAI, and then we're creating the service context, which lets us use the LLM that we just called. I know this is all very confusing, but this is just how the framework is set up. The storage context, basically we're saying, hey, we created that vector store earlier, use that vector store we created earlier. And now we're going to create 2 more dictionaries, right? So earlier we created a dictionary that linked the name of the city to the documents that are created for that city. Now we're going to create one that creates a link between the name of the city and the vector index created on the documents, okay? So now what we're essentially doing is we're essentially saying like, hey, you remember that city, you remember the documents that we created for it, let's vectorize all those documents and put them into a vector store. And then we link them together, and that's what this is. And then what we do for this part, this is saying we're going to take those cities and we're going to give them a summary, which is essentially what the keyword table index is going to be. So these are the keywords that the application will look for when it's looking for the right vector store. So clearly Wikipedia articles about XYZ is a bad title, but for your cases, what you want to do here is put in some keywords here that make sense for you. So does everything make sense so far? Are there any questions about this? Everyone good? I see some thumbs up. Can I see some thumbs up? Everyone's following along? Everyone understands? Okay, cool. All right. Oh yeah, let me run this actually. Oh, I broke this. Well, that's embarrassing. Okay, well, then I'll just walk through the rest of the code and I'm not going to run any of it. So now what we're going to do is we're going to create that graph, right? So earlier I showed you this thing. This is essentially a graph, right? So now we're going to create that graph. I actually know what the problem is here. I'm not going to fix it live. Okay, we're going to create that graph. And what we essentially want to tell that graph is we have a keyword table index. And we also want to get the city indices. This is the vector store indexes. And these are the Wikipedia article about XYZ indexes. Okay, so now what we've done is we've created a graph that maps the keywords to the vectors to the keywords that are in, the keyword index to the vectors to the keywords. Okay, everybody understand this part? Does this make sense? No questions, okay? Yes. Where are the keywords coming from? Great question. So before I broke this, we had this line here that says index summaries wiki title equals Wikipedia articles about wiki title. This is essentially what's going into your keyword index. Now I realize this is not a good keyword index, but this is just an example. This is a toy example, and this is what's going into your keyword index. So this is how we created those. These are up to you to create. The keywords are up to you on what they should be. Okay, does that make sense? I don't know who asked that question. Does that make sense? Cool. Okay, so now we're going to create the query decomposer, right? So earlier I said, hey, one of the first things we hit is this query decomposition, this query decomposer. This is a query decomposer. All we do for the query decomposer is we pass in the LLM and we say, hey, use this to decompose the query. That's all. That's it. That's all this is. Okay. Now we're going to create our 4th dictionary, and this is the part where things get like really weird. because what we're going to do is we're actually going to go and we're going to loop through all those vector stores. And we're going to use each vector store as a query engine, just as like we did in the last example that I showed, the very simple llama index example, if you guys remember. We're going to use each of these as a query engine, and we're going to pass it the LLM, and then we're going to add some extra data to it. So what this line does is we're adding in this index summary, and we're saying, here is the index and the index structure for the keywords, basically, okay? Then we're going to use the transform query engine. This is a built-in function for llama index, and we're going to put in the query engine, the decomposer we made, and this extra information. Then we put in the index ID, the ID of the vector indexes, as the keys to our custom query engine. And we're going to set the values to the transform query engine, which means this is the query engine that has access to the query transforms, the query decomposition, okay? Does it make sense? Does anybody want me to repeat this? Okay, I'll repeat this. Okay, so remember, we have a set of vector indexes. Now we're going to use them as query engines, okay? So we have a set of vector indexes, and we're going to query along those indexes. Then we're going to add this here so that we can map the keywords to the vector indexes. So that's essentially what these two lines here are doing. They're allowing you to transform your query using the query decomposer so that you can map the keywords to the vector index. So this line here, what it's doing is it's creating this stuff right here, these lines. Okay, does that make sense? Okay. And then we're going to put that into another dictionary so we can keep track of it. That's all this does, okay? Then, and this gets even more confusing, we're going to put another thing into our dictionary that contains all these indexes, and we're going to give it the graph, right? So now what we're doing is we're at this part, and what we're saying is, okay, now I'm going to show you this entire graph. So we're starting with the root node of the graph, and this part doesn't really matter. All you need to know is that this is a way that you can retrieve that graph stuff, and this gives that graph access to the LLM. Finally, the last thing we're going to do is we're going to get our query engine decomposer. This is essentially this whole block here, this entire block here. Everything but the query is now what we've just created, is we're about to create here. We're going to use the graph. Remember, the graph was all the lines that were pointing towards each other. And we're going to use that as a query engine, and we're going to feed it this dictionary so that it knows how to basically map those routes. And that's it. Once you have that, it's really simple. All you got to do is you add it, ask it, compare and contrast the airports in Seattle and Houston. I haven't been to Houston, but this is just what I chose for this. And it'll give you a response. Does anybody want me to repeat any of that? Because this is it. This is the end of the presentation. Does anyone want me to repeat any of that? No, okay. Oh, yes. Yes. So we're going to map this here, right? So this is essentially saying, like, you should know what these keywords are. This is essentially giving it access to these keywords. The keyword indexes, sorry. Right, index.index struct. It's giving you the structure of these indexes. Oh, sorry, I keep touching my computer. It's giving you the structure of these indexes. Yes, 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 yes. Okay, so yeah, that's the end of it. Hopefully, you know, that may, oh yes.
So if you had actually run the code, what would the output have been?
If I hadn't broken this earlier, and if I had checked this earlier to see if it was broken, I probably would, you know, would be able to tell. But it would say something like, you know, the airport in Seattle is the Seattle Tacoma Airport, and it has, you know, has this many terminals and this many planes fly in and out of it or whatever. And then the Houston airport Houston actually has like 2 airports or 3 airports. Houston has XYZ airports, and, you know, this is how big they are, and this is how many terminals they have, and stuff like that. Yeah. Yes, guy in the white shirt. Yeah, that's a really good question, because you're going to kind of want to route each query to a specific document or set of documents. And that's actually kind of, that's an unsolved problem, right? That's a specific, very like, if you're an enterprise, that's up to you to solve that problem. And I mean, like, if you have specific questions, we can talk about this later and I can give you my thoughts on that, but that is much more of a bespoke question. Yes, the woman in blue. Okay. In this case, we have however many are in the size of this list, maybe like 10, something like that. Cool. Okay, so Bill is cutting me off. So for those of you who have questions, I will be back there and you can come talk to me back there.
Great, thanks. Let's go. Actually, I have a last question. Where's the socks?
I left the socks in my backpack. Normally I have socks. No, they're not in my backpack. Normally I have socks, but I put them in my duffel bag when I flew yesterday. So they're in the duffel bag. Sorry about that.
All right, thanks, Yugen, for the presentation. So our next speaker is Josh. He going from. Okay, I think that sometimes somehow they mess up the camera things. So our next speaker, Josh, he come from Trero. He going to talk about the evaluation builds better AI agent. So without further ado, let's welcome Josh.
Thanks, Bill.
Just go to the room.us website, the room website. Yeah. Don't.
Good deal. All right. Hats off again to Eugen for the awesome presentation. So I'm Josh. I'm a DevRel engineer at Terrera, and today I'm going to try and convince you that evaluation makes for better AI agents. So there's been a tremendous wave in developers building LLM apps. We're building apps like question and answering chatbots, code generation copilots, and enterprise search. And we build these by composing models like GPT-4 and Llama 2, vector stores like Pinecone and Milbus, and links to the real world when we want to really step it up, like plugins and agents. And we put this all together using frameworks like LangChain and Llama Index. So how do people test AI agents today? First, we build our agent. And then a lot of times we hope and pray that it doesn't destroy the world. So hopefully we can try and do a little bit better than that. And this is why we built TrueLens. So TrueLens is an open source project to help you track and evaluate your LLM experiments. So once you've built your LLM application, we'll connect it to TrueLens and start logging records. So that way, each time we run our application, we can get the prompt, response, and metadata and log all that so we can keep track. Then we can add what we call feedback functions to evaluate these prompts, response, and metadata. And this can give us a score or a view into how our app's performing. Once we've done that, we can explore the records, evaluation results, and chain versions in our TrueLens dashboard. It's going to look something like this, and this will run locally on your machine, or it can run from a SQL database. And then from there, we can iterate and select our best app version using all of the evaluation results along with key metadata like cost, latency, things like that. Hopefully, this is slightly better than hopes and prayers. So there's a range of AI agents that are possible. So on one end, we have specialized AI agents. And these are similar to your RAG style apps that Eugen went over, except they have access to real-time information. So maybe they go out to an API and fetch information from there. Moving on to general data agents, these have access to more than one tool, and we can accomplish a wider range of tasks with these style agents. And then last, we have agents that can take action in the real world. These agents can book plane tickets, create calendar invites, and more. In today's talk, I'm going to focus primarily on specialized data agents, and this allows us to limit the amount of things that can go wrong and really focus in on solving a few key problems. And this style of agent is better than just using your typical LLM call. So if I ask, what's the best Filipino restaurant in New York City, I get this classic data freshness problem. Our training data is up to only a certain date, and I can't answer questions past that. And a lot of times when you build RAG style applications, you have the same issue. So your vector store is pulled from documents and information that are still only up to a certain date, but you want access to the most fresh data. And that's where these AI agents come in. So data agents for real-time retrieval, the architecture is going to look something like this. So our reasoning agent is going to sit at the center, and that's going to take the user input. Taking in the user input, it's going to then choose a tool and form the input that's required to go into that tool. This tool could be anything from the Yelp API to Archive to Slack, Reddit, or Yahoo. And then once the API returns the response, it can pass it back into the reasoning agent, and the reasoning agent can form that into an intelligent response, we hope, to the end user. All the while, we're writing this to our conversation history. But there's a bunch of failure modes that can go wrong here. So the first one could be we choose the wrong tool, or we send a bad input to the API. And this is what we call a rogue path, where it can go off astray. Maybe the LLM answers the question without using a tool at all. We can also get into this infinite loop problem. We saw this a lot with, especially in the early days of agents, where we had baby AGI or like God mode. They'd kind of get stuck in this like loop and never really get done the thing we wanted it to get done. We can also have failed API calls. So with all these APIs, there's a whole bunch of new things that we have to worry about. So maybe Twitter adds a giant cost to each time we call the API. Well, that's a problem for our app if we need Twitter's data. Maybe Reddit has a moderator strike, so we don't have access to those subreddits anymore. There's a whole bunch of things that can go wrong and that we have to now worry about here. And then the last problem I want to talk about is hallucination. So hallucination is maybe the problem we're most familiar with, and this applies to all kind of just simple LLMs along with RAG style apps and agents. And this is when our agent or LLM confidently responds with the wrong answer. So everything from here on out, you're going to be able to follow along using a Colab notebook, and that's going to be the QR code here. So I'll go through it in slides first, and then I'll show you the code after we get done with that. And give everybody a second more to scan QR codes as we're still got phones up. And this example also is going to be in our GitHub repository, so you'll be able to find it there too in case you miss it. All right, I think most of the phones are down. All right. So here I'm going to build a data agent for real-time retrieval, and specifically we're going to make it concrete with the restaurant information chatbot. So here we're going to use the Yelp API as our knowledge source. And once we feed in our user input, oh, I forgot a key detail. So we're also going to make this respond like Gordon Ramsay. So our reasoning agent is going to take in our user input, translate it to a query that's acceptable by the Yelp business search. So that's going to be like a small string that Yelp can use to find relevant restaurants. Then Yelp's going to go out, return some restaurants, some information, some ratings to help you answer that question, and pass that back to our reasoning agent. Then our reasoning agent can take that information, that context, and turn it into a final answer that your user is looking for. So one of the advantages of a structure like this is that we're able to test kind of throughout the app. And so if we go over here, when we have this kind of user input to translated query, we can test to make sure those are kind of conveying the same information. When we go over here to get to these Yelp API results, we can make sure that the API results are also relevant to our original user query. When we get our final response that the Asing region comes up with, we can make sure that every statement that's made by our agent is fully supported and backed by evidence from those API results. And last, we can make sure that our user input and returning response are also relevant to each other. And we're going to go through that in a little more detail. So as I said, this is going to be Gordon Ramsay style. So the first eval we need to do, like I mentioned, is query translation. So this is checking in the past from the query to the agent. Is the information that comes through the query matching the information that goes to the agent? So we're going to use TrueLens for this evaluation. And basically what we're doing here is just calling another LLM and saying, are these two questions kind of saying the same thing? So in this case, the question 2 is what's getting passed to the Yelp API, and it's just like a smaller string taking out the irrelevant information that Yelp doesn't need. And this gets a score of 1, so that's a high score. This is all good. So the next thing we want to check is what we call context relevance. So context relevance is taking the context that's retrieved by the Yelp API and making sure it's relevant to the original user query. So a good example, we ask what the address is of Gumbo Social in San Francisco. The Yelp API goes out, returns this address, and then we check and make sure that this is actually an address, that this is relevant to the user query. So we get a good score here. Groundedness is a tricky one. So this is where we want to make sure that the response that the LLM returns to the user is fully supported by the evidence we supplied it. So here's the first is a simpler good example. So this is the same kind of question. We have this evidence, which is our address that was returned by the Yelp API. And then the LLM is taking that and forming it into this kind of nicer response. The address of Gumbo Social is address. And this gets a good score. So here's a slightly worse version. So here, this is the kind of groundedness reasoning. So here, these first 2 are pretty good. These are broken down by different statements that are supplied in our final user answer. So this first one about it being subjective and based on personal preference, that's backed up by the evidence. You can see it here. We also have the list of diners That's also backed up by evidence. But then, then our LLM goes all Gordon Ramsay style, and it says, I recommend trying them out and deciding for yourself what you like the best. Just make sure you have low expectations, as most diners in Toronto are mediocre at best. I haven't had any diners in Toronto. I don't know if this is true or not, but the key part is that there's no supporting evidence from the Yelp API that supports this claim. This gives us a low score. So even worse, here's one more example. So here we have one good statement sentence, which is the list of best pizza places in New York. And we asked it, what's the best pizza in New York? And then you can see we have a bunch of kind of essentially made up statements about if they're known for delicious and authentic pizzas, no evidence for that. That Rubriosa offers a variety of thin crust pizza, no evidence for that, yada, 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 no evidence for a bunch of these. So we have a really low score on the groundedness of this statement right here. And the last thing I mentioned is this QA relevance. So here we're checking, once we've gotten to our final response, is that response relevant to the original user's query? Is it going to be helpful? Is the user going to be satisfied with that answer? So here's an example of what that looks like. So here we're comparing the end response. The address of Gumbo Social is addressed. Now do yourself a good favor and go enjoy some gumbo. This is relevant to the user query, so it gets a good score. And here's a slightly worse one. So we asked it, what's the best diner in Toronto? We talked about this answer already. It's like mostly relevant to the user query, but maybe people aren't always happy with this response. So data agents give us more certainty to eval by giving us the ability to test throughout the application. And thorough testing of LLM apps helps us ensure that we're not hallucinating. So now I'm going to jump over to the code and show you how we put that agent together. Any questions so far before I go on? Cool. I'll continue on. Yeah. Automatic. Yep.
Like, what application does it scale to?
What do you mean by that?
I guess like what cases can it generalize to, like the automatic grading? My guess is like the complex, as the complexity of the question and the task of the research agent increases, I'm assuming the ability to automate code apps.
Yeah, you're kind of like limited by the ability of like the model you're using to grade. So as we get better and better LLMs, we can also do better grading. We do some of the grading with like kind of older models, classification models, things like that. So it kind of just depends on your model. That's your like limiter. Any other ones? Good deal. All right. So here we're going to use Llama Index to build our app. So the first thing we want to do is we're going to import this Yelp tool spec. And that's just going to be the primary tool we're going to use. And then we're going to also import this load and search tool spec. So this is going to allow us to load in our app. Yeah. Oh, yes. I should have known that from the first talk. Let's see. Is that good? Awesome. Awesome. And then now what we're going to do is create our OpenAI agent. So we're just going to kind of pass in the tool we need. The Yelp tool is kind of weird in that it requires kind of both tools, but it's really just one. It's kind of a weirdness there. And then importantly, we'll also pass in this system prompt. So this is this like telling it to act like Gordon Ramsay. So let's run some stuff. Awesome. So we're also going to create a standalone LLM for a comparison, and this is going to give us the ability to kind of just see how much better our AI agent is compared to just asking ChatGPT. Okay, so next we're going to import some things from TrueLens. So this is going to give us everything we need to do our evaluations. So pointing out a few things here. So True Llama is going to be our integration with Llama Index. This is going to let us kind of instrument the different components of the Llama Index call. So we can see each time it does a different thing. Each time it passes through the application, we can see everything that happens, track the cost, track the time, all that good stuff. And then importantly also, we'll import a couple feedback providers. So here we're going to use OpenAI to do a lot of our feedback. So this is kind of OpenAI from TrueLens eval. And then we'll also have groundedness and ground truth agreement. So I've already run this one. And basically this true.run dashboard is just going to start this local Streamlit dashboard. We haven't put anything in it yet, so it's empty so far, but that's what that does. And at this box, there we go. All right. Okay. So the next thing we need to do is set up some of our feedback functions. So the first one we want to set up is the query translation score. So this is going to be a custom one, so not out of the box, but it's really simple. So all we're doing is prompting GPT 3.5 to say, your job is to rate how similar the two questions are on a scale of 1 to 10. Respond only with the number. And then we'll get that response divided by 10, normalize it so we get a nice 0 to 1 score. And bada bing, bada boom, there we go. And then the second one is kind of more of a app-specific requirement. So we didn't talk about this in the slides, but say we want to make sure that the context that the Yelp our app is using from the Yelp API always has evidence or ratings mentioned to support it. So that's what this one's going to do. And let's run this guy. And then we're going to pull in some from out of the box. So we initialize query translation and ratings usage. And then here we have QoS relevance, question statement relevance. This is the context relevance that we talked about in the slides. And kind of importantly here, so we have this select.record.calls. So basically what we're doing here is that in different apps, the context sits in a different part of the call stack. So we need to kind of go in the JSON and figure out where's the context we want to check, and then locate it with this kind of select helper function. The second thing is just checking the input and output. Here, this is the question answer relevance that's right here. Groundedness is kind of similar. So here we want to take the same context that we did here, right here, and then we're going to want to check it against the output on output, and then we want to aggregate it. So here we're going to use the custom aggregation, and it's going to result in the thing you saw in the slides. So let's see, we ran that one. And then one more evaluation that we're going to do here. So a lot of times when you create your LLM app, you will have a kind of few key prompts that you want to make sure you respond well to. So that's what we've done here. We've just set up kind of 6 golden set records. Obviously, a toy example, you'd probably have more than that. But this is just an example of what that looks like. And then we'll kind of construct our feedback function from there. So we have ground truth agreement. We'll pass in this golden set. And then we'll say, we want to test to see, is the response that our app comes up with similar to these responses? And we'll test that on input output. So from there, we can run our dashboard like we already did, and we can construct our app. So here, we're calling True Llama, passing in. So this is our agent that we created with Llama Index. We can give it a name, give it some tags, And importantly, we'll pass in our list of feedback functions. So these are all the evals we want to do. And then similar process with the standalone app. So here we just want to instrument these plain old GPT 3.5 and get some evals on that too. Then we'll set our list of prompts and run all of these prompts through each app. So as this runs, I'll switch over to our dashboard and we can see these kind of start to come in. Yeah, so here you see we have the first one. This is just with regular GPT 3.5. We have our first record, got pretty low score on both relevance and ground truth. You'll note we can do a lot less evals for this one because we only have access to the input and the output. We don't have like access to all the internals like we do with the agent app or like we would with a RAG style app. I can refresh, get to see if we got some more. Yep. All right, so it's like we're still waiting on some evals. Okay, here we go. So now we have the full suite of evals for the first 2 records with the Yelp agent, along with 3 with the OpenAI agent. So you can see we have evals for groundedness, context relevance, query translation, rating usage, ground truth agreement, and question answer relevance. And we can kind of look at what those look like. So we can select the app and then examine those. So maybe we want to see a little bit more about this, what's the best pizza in New York. So you can see kind of the breakdown of how all these evaluations happened. For the groundedness, what's the reason? We can kind of click on expand any of these like that. And last thing I'll show you is we can also see kind of a timeline of how this app is working. So we have our Yelp agent. The first thing it does is calls the OpenAI agent. That's kind of going to run the whole length of the rest of the app. And then in the middle of here, we're going to use a query engine. And that pretty much covers it. So from here, I'll just go back to the slides. So you can find TrueLens on GitHub. We're fully open source. So I'd love if you check it out and I'll take questions from here. Yeah.
You had an example of an address as being a thing that was supposed to be correct.
Mhm.
How reliable is the checking of that? So I imagine addresses can have different formats.
Yeah.
If you have something in a different format, that's fine. But if you get like one of the numbers wrong on the street, then that's completely wrong.
Yeah.
So how does that work?
Yeah, so what we're really doing there is like we're checking to make sure that the address is like relevant to the question. So we're not saying the address is like correct necessarily, but it is an address. And then we're kind of relying on the like correctness of your like API that you're calling to kind of do that. So we're like narrowing down the problem area. So if all of these are right and your source is right, then you're correct. Good question. Awesome. Yeah, in the back.
Couple of questions. Question one, can this also help on debugging long cheats? Because right now the only way is like to stack them on a file and see where you want.
Mhm.
So that's question one. Question two is you use an evaluation model for scaling between 1 and 10. What's kind of like the hallucination you have seen? Like, because your calls does it grade something as 8, but the next call it grades something 7 or 6? Like, what's been your sort of observation?
So the first question, it's really great for long calls because we can see kind of like we did, like here we can see kind of how the app is working, what are the different calls it's making, if there's any latency, where's like kind of the latency being introduced. And then on the second question, I think you were asking about like the hallucination of like the grading. That's a good question. So we've done a few kind of tests, and this is still pretty early on kind of grading the graders. So far we focused this on like our relevance tests, and we've done it at a pretty small scale. And basically what we're just doing is we're saying, there's maybe like 10 kind of question statement pairs that we want to make sure are in a specific range. So that's something we're testing with every release. In general, I'd say it does worse when you have longer context that it has to check. It tends to kind of focus on the beginning and the end. There's some prompting you can do to make that a little bit better, but that's definitely a challenge for sure. Yep. Awesome.
How is evaluation, how does it work after the ultimate relevancy is not score and chips similar words without ethics? So how do you determine two chunks of text or
Yeah, so we experimented a bit with things like blue scores and stuff, like you mentioned, but we found that kind of LLMs were like better at doing that themselves. So you're really just kind of doing it by prompting. You're saying, is this text similar to that one? That being said, you can plug in kind of any, if you have more of like a classic classification model or something you want to use, you can plug it in there. It's like pretty extensible. But short of like having a human to like individually grade each one, we find that LLMs are pretty good. Does that help? So we're doing it like by prompting. So we say like, hey LLM, I have this first statement. I want you to rate on a scale of 1 to 10 how similar it is to this second statement. Awesome. Any others before? Yep. Mm-hmm.
Have you guys played around with different LLMs in the process of building this tool? Have you found differences between the LLMs you're using and what their efficacy is? Do you have any future plans against hallucinations on longer chains?
Yeah, so that definitely falls in like the future plan bucket. So we haven't done a lot of comparison across like different grading models yet. So that's something we're trying to do in the next like month or so, especially as we kind of introduce the like more built-in models to do this grading. So I'll have to get back to you on that one, but awesome question. Good deal. Cool. Last thing I'll plug before I pass it back to Bill is I have some like stuffed llamas that I'm gonna go get from the hotel right after this, and I'll have like 30 of them. So if you want, they have a cute little t-shirt on them and I'll be passing them out. So that's it.
All right. Great, thanks. Okay, thanks. Great presentations. So let's move on to our next speaker, Mary. She's going to talk about vector search, I think. And Mary, she comes from data stacks. Yeah, we're going to take a few seconds to set it up. Yeah. First, join the room. This is the room meeting ID.
Oh, sorry.
Yeah.
So I get about 20, 25 minutes.
Yeah, 25 minutes.
Okay. That's right. Oh, yeah, I'm connected.
Yeah.
I don't know what is going on. Okay,
Just join.
Yeah. Okay, ID.
And 592 368 6112. Yes.
Okay.
And join and then share screen.
And no audio.
Yes.
Or do you need, like when you record, you'll be able to
join.
Oh yeah, so you'll be able to.
Yeah, I will capture that.
So turn off all the audio.
Yeah. The audio will come from here.
Okay. And then without audio.
Yeah, that's fine.
Got it. Okay. Okay. Oh yeah, and then you have that. Okay, or maybe clip it, right? Yes, so you have a good size. Like a, yeah. Hello.
Share
Okay.
screen.
Yeah, oh, yeah, share screen. What here? Sorry.
Oh, you already shared?
Not yet. Oh, yeah, that's.
So it's
Oh,
probably another screen.
wait, another screen. Yeah. Let me see. All right, I have to go to pick this guy and then. Oh, maybe it's actually it's this one. Let me see. Let me hold on. Let me slideshow it first. I wonder, and I go back.
It's showing the other screen.
That's right. Yeah, let me. How do I go back to my Zoom to tell it? I lose my Zoom control. Or oh, Zoom. Yeah. Share screen. Maybe this way. Yeah. Okay. Oh, here we go. That's it. Yeah.
All right.
Okay.
Coming up.
As long as that comes right. Yeah. Oops. But then I won't be able to see it though, right? Oh, let me. I should.
Okay,
Oh, here we go.
yeah.
Yeah. Okay. Great. Yeah. Thank you.
All right.
Thank you. Thank you. Thank you very much. All right. Yeah. Good. Yeah. Okay. All right. I guess you can all see. Right. Okay. All right. Great. Yeah. Okay. So should I wait for folks to, is it a little break now or I can just start? Okay. Yep. All right. So thank you very much, to stay and listen to my talk. Okay, just the first thing. My name is Mary Grigleski, and I work for, as Bill mentioned, I work for DataStax, the company. I think, let me ask too, how many of you have worked with Apache Cassandra? Have you, by any chance, Apache Cassandra? So maybe just a few. That's a NoSQL database, and it's Apache, so open source NoSQL project. And so DataStax is very much involved with that. They're founders of DataStax, the commercial company that actually we support. We have committers, PMC in the projects to program committee. So we are kind of leader in Cassandra. So recently too, like with all the AI, the chat GPT, all of these things, Gen AI. So our company also we're supporting vector search, vector DB in our Cassandra database. Now, for me, I'm a developer advocate, and I do have to kind of give you a bit of a warning, so to speak, because I was actually with the streaming team before. So I work on event streaming, like Apache Pulsar specifically. And how many of you, I'm just kind of out of curiosity, do you work with event streaming, for example, like streaming? I know Tim. So Tim, yeah. Okay, so maybe, okay, so it's not an issue. So it's interesting too, just to kind of give you a bit of I said warning is because I kind of recently too, also the whole company, we have to talk about Gen AI. And happens that today, our company did a free webinar. I see that it's on AI Camp being advertised. I love AI. So none of them are ready to do presentations. So they asked me and I just switched to the team. So bear with me too. I'm kind of just gonna be doing a bit more of, enter the brave new world of Gen AI with vector search. So I'm not gonna go very deep into, how you do things, but I want to introduce to you to the capability that our company has, right, with respect to vector search and vector DB. And may I also see a show of hands? How many of you are already kind of deep into working with AI? I just want to get a bit of a understanding. So, okay, so bear with me too, because some of the things are just more introductory, because at the same time, I'm also learning. So maybe not, all of you are kind of expert level, so bear with me. So that's it. So enter the brave new world. I call it brave new world because that's become such a, the phenomenon as such, right, in recent months. So again, I'm a developer advocate. So this is the agenda that I have for today. Just a brief background introduction, brief background of AI and getting into fascinating the evolution of Gen AI. And also GPT, that's kind of, we want to kind of sort out all these terms first. Natural language processing, LLMs, all of these, just gonna go over it, and then I'll introduce to you vector DB, and as such, it's only 20 minutes, but I want to also quickly show you how you can actually use and do something with vector DB using our DataStax platform. As such too, it's also a free kind of $25 per month kind of credit. That's enough for you if you want to do personal development. We don't ask you for credit card type of opportunity. So it's not just like, okay, I do and I go home. You actually can go and try it out yourself. So that's the goal. And then some benefits, right, and challenges of this technology too. So that's the plan. All right. So first, introduction. So I'm a senior developer advocate. As such, I was working more with event streaming with Apache Pulsar. I also am very much involved with the Java community. So I'm also Java champion too. So I'm actually somewhat new, I have to admit, to more of AI, machine learning things. So you can help me too, if anything I said wrong. So I also run the Chicago Java users group too, if you're interested in following us. And I work with Pulsar and also reactive systems and event streaming. And I was at IBM previously as a developer advocate in Java side. So, but I'm finding this to be such a fascinating topic that I think we all get pulled into it, like it or not, so to speak. But I'm glad too. I mean, now the opportunities present itself to me. So that's about me. Okay, so a brief background, right, of AI. So I just kind of like wanting to kind of get a more understanding of this topic area. So kind of looking into AI, in fact, I found, this information, right, it's really about AI, it's about automation, if you kind of think about it. So as early as 400 to 500 BC, if you want to count that, there was actually a steam pigeon, right, mechanical. So that's how the world kind of started. I think that would be counted as kind of an artificial intelligence because it's mechanical, but it's kind of robotic in nature. So that's what it is. It was, basically invented by Archytas, who was a Greek philosopher. So, and now, like in the near old times, in the 20th century, if you kind of look into the timeline too. So these are the different things, right? Basically, there were science fiction, a lot of all these questions too about can machine think, and Alan Turing, the famous computer scientist, and all of these, and the different research being done in the 30s, essentially too, like, since the World War timeframe, I think it's just kind of like shot up to all of these, and then the research being done at MIT. And in fact, when I kind of think about it too, I don't know if anybody have used Emacs, this editor, right? It actually was developed at MIT, the AI lab. And at that time, the AI too was very much kind of the older style of AI. There are just so many branches as I'm learning. But I remember too using Emacs, that editor, right, the text editor. And there's lots of functionalities, and one of which actually you have to ask the doctor or something like to cure your problem. So that was already using a prompt way of doing, like, it's really an early form of GPT, like in which, chat kind of thing. And I remember I was trying it out at the time, maybe in the 2000s, with saying you just ask, saying something is wrong, and then it comes back and say what is wrong. It keeps asking you. So a different way of asking about, things, and like a prompt and response type of kind of manner, so to speak. So, okay, so then this is kind of like the 20th century. But again, this is really all about, when I kind of think about philosophically, it's really we're trying to look for ways to automate all of our work, especially when you kind of think of it, AI can be applied to so many different areas. So it's really about automation. And then also just a bit of a kind of the Venn diagram, so to speak, about this whole field, right? Generally speaking, we have AI, which actually is more of an umbrella term that covers inside it a subset of machine learning that actually then much deeper is going into deep learning, the neural part. So the really outside part is a bit of a higher level abstraction that is making use of computer to solve your problems, right? And then it gets into machine learning, in which you're training, the system. There's supervised and unsupervised reinforcement learning, that kind of techniques that you can train the machine to learn, and also to do different, produce different results following some kind of complex rules too. So training the model from different data sets. But as you kind of dig deeper, is that, the machine learning is more computer level, while deep learning, getting into it. Actually, one thing I think should have been is probably the neural networks side, in which is actually we're mimicking how neurons think, how human brain functions too. So you'll be able to do sentiment and all of these things that are much more difficult to kind of like generate results based on those data. Okay. Okay, so now then kind of jumping forward now, right, without dwelling too much into the old stuff, but it's good to know. And anyway, to kind of look into it, right, generative AI, Gen AI is like the talk of the town now, I guess, since ChatGPT came out from OpenAI in November of 2022, so less than a year ago. And as such too, we all know that it became like such a big phenomenon. Like millions of people sign up and kind of essentially crash their servers. So because they weren't expecting so many people to be using it, right? So it's really exciting, as you can see. So really kind of taking a look into it, what is Gen AI, from the ground up, is basically a very disruptive field in AI because, well, it has the potential to change the way how we kind of grab data, right, create content too, and then also kind of consume the content and create new things that already it is surprising us every day. So essentially generating new contents based on prompts. So I kind of call it like, ask and you will receive, seek and you will find, this kind of thing, that if you kind of think deeper on it, I like to think of philosophy. So it's kind of like that. You ask and then it helps you. It comes back with some response. So essentially, too, Gen AI combines machine learning and neural networking to kind of solve problems for you and produce contents for you. And also, too, kind of, when I was doing research, too, then there's also predictive AI, too, that's kind of more popular, so to speak, right, before Gen AI, which is actually the way I look at it and also doing research is generative AI tends to be focusing more on the creative kind of longer term side, so to speak. We all know it can write the essays for you. It can, compose music for you too. And I guess on the, if you're taking not the text form, it's actually can do a lot of artistic things for you, design some fashion, doing some of, these things that basically takes away all the grunt work and does things for you quickly. Whereas then for predictive AI, it's more about a bit of a shorter term, so to speak. It's about forecasting. You're taking some data and then it analyzes it and comes up with some analysis, more analysis based, perhaps to the, it doesn't last as long, the need for those data. It's more like weather forecasting goes away today, you don't care about it anymore. Tends to be predictive side, right? And generative side is taking some information, it can figure out your sentiment, and that's kind of really most valuable. How can anybody figure out, right? How can you guess what a person is feeling? Those kind of things. And even between humans, we can kind of figure out. So we're trying to get machines to take care of that for us. Now, look a bit more, right? And since the new millennium in 2000, right, kind of jumping a little further out, basically, these are just a couple of lines of things I was looking up, In 2003, essentially, it's already guiding us towards that. The current time is Joshua Bengio and his team developed the first feed-forward neural network language models. And then essentially in 2011, so just roughly 10, 12 years ago, then Apple brought out, the Siri, which also like kind of moving us closer to that with NLP assistant too, that type of kind of involvement. And then in 2013, it's basically the group of Google researchers led by Tomas Mikolov. They create the word-to-vec, and that's actually, technique for natural language processing that uses neural network and to learn the word, from a large sets of data. So that's also kind of very relevant to today's, kind of leads to today's doing all the vector search, all of these things. And then in 2017 will be also Google researchers did like the new simple network architecture, the transformer. And now then it kind of then leads us, right? It's really GPT kind of started, if you kind of think of it too, is basically what it is first. So it's really about taking some prompts, right? And then in natural human language way as input. And then you actually, essentially too, I kind of always hear people saying it's a search. Of course it is search, you large amounts of data you are searching. But what it really is really pattern matching. I was also talking with another Java champion too. He's saying that if you think about it, right? If you're doing like, especially on the coding side, right? You're doing coding is a lot of just pattern. You're finding patterns in all of your data. And then you feeding it some prompts and it's looking for what you're trying to search and then do some sort of pattern match based on your input. So, but it's kind of close enough, you can call it a search. And essentially, too, GPT can answer your questions, right, based on your prompts. And so it can produce contents. As I mentioned, you can write an essay, write a blog post and a new computer programming too. And so maybe that's where also the very controversial, because you can be doing things that is unethical. Nobody is there to check it right now. And so that's kind of the danger side of GPT as well, as we know. I think it's just like anything else, right? If you put it to good use, it's great, but there are also some kind of bad elements out there, as well as perhaps like unintentional bad use of that technology. So that's something we need to be also worried about too. So we look back now, GPT is really, when it becomes more the thing is really since 2018, right? It's the Alec Radford's paper on GPT, right? So it's basically republished on the OpenAI website. And so that's when it started kind of becoming the thing. So it's roughly 5 years ago, really not that long ago. And then in 2019, immediately, it already OpenAI released the complete version of GPT-2, which was trained on a data set of more than 9 mission documents too. So it's kind of slowly expanding. It's actually interesting when I look at it, it's about COVID time that it really, the GPT thing becomes like all fast growing. Maybe all the researchers have more time and then they're like focusing on doing that. So anyway, so in 2022, just roughly a year ago, right, was the Stable Diffusion too that comes up with deep learning text to image model. So it's just kind of all these things like suddenly kind of took off. And then, of course, GPT 3.5 in 2022, right? That was the thing that kind of wows people, starting to be like that. And then 2023, the current year, we are seeing a lot more technology being competing with one another too. Like that includes, BART and then ChatGPT and all of these things that comes out too that we all are so familiar with. So without me having had to repeat again. So, but as you can see too, it's just there's just much more things that are happening as we speak too. So I don't have to mention it all. We're already following it. So now let me then get into the next thing is basically natural language processing too. So that's basically what it is, right? It's really an interdisciplinary kind of field that's between linguistic and computer science too. So the concern is basically you want to process like natural language data sets, such as like text or speech, kind of huge bodies of data in it. So, and then it uses like rule-based or probabilistic like machine learning type of approaches. And the goal is to try to enable computer, again, to be able to analyze, right, learn from the content, and then including that contextual differences, the nuances of the language itself too. And it's really kind of goes beyond just that mechanical part of analyzing thing. You want to again, draw insights that's beyond just the obvious. And then large language models, as I don't have to spend too much time explaining, already we have folks, Josh and I think Tien-Tsin, who already give you examples much deeper on that. But really what it is foundation type of model. So it's foundation, but also the thing though is that, yeah, you can do a lot, but if you think about it, the pre-training part of machine learning, it just consumes so much resources, as we know, like, a lot of money have to spend on all the GPUs. And not only that, all the amounts of data you need to crunch through will take weeks, if not, months or something to go through. So it's actually very expensive too. So it is the thing that I feel there's a lot more research can be done to lower the cost, basically, in this too. So again, large language models are essentially the ones that's leverage or the way I'm like sorting it out is NLP, right? Natural language processing is the way you do things at enabler. But yet LLMs are the ones that actually performs the task of an NLP in order to generate all of these models. So now then let me get to the vector search. I always talk too long. I realize I don't have as much time. So vector search and vector DB as such, right? We know that this has become even more important these days because, again, we deal with so much data, and then I don't have to repeat again, in which it relies essentially on vector embeddings, and I think the previous two presenters did a great job explaining, so I don't have to explain all of these things, in which, it's basically you have to look at data in the new ways, and essentially making use of vector to do all of the processing, do all of the search, because these are just happens to be new ways of doing things. And you need to be then parsing your data, you do need to essentially assign them numeric representation to your data in order to be able to enable, the fast pattern match. That's what it is. So, and then it's basically, two of you describe it, it's also an automatic form of feature engineering. As you know, feature engineering are like, you're taking all your data essentially to absorbing what is important. You generate that kind of set of data that's actually useful for you to do further kind of inference kind of processing too. So another thing just want to mention too is that, of course, there are techniques that is doing when you do pattern matching is slightly different here, is making use of the, many techniques, right? So for what I know is that at DataStax 2, we have using approximate nearest neighbor, ANN type of algorithms to do all the approximation of finding matches, right? So that's the thing I wanted to kind of bring it up. So let me see. So there are like benefits. I kind of already thought of this thing is like basically you ask, it's very much of a prompt generated type of system. You ask and then you shall receive, and then you seek for it and you will find. I feel like that's what the benefit is. You always have received some answers from what you ask. But the challenges are there, as I mentioned too, and folks kind of talk about hallucinations, right? Then you may not be getting correct answers. And that's where I feel too, with Gen AI, people, and I'm sure you have also heard of, there are people that are fearful that, well, what if our jobs go away? Now it's gonna be, GPT, AI taking our jobs away. But no, if you think about it, that means we're being overconfident and thinking these robots can do our job. No, they make mistakes too. And in fact, I think there were also like examples of them answering the wrong thing. Like, I think a simple example, I was doing a recording for a presentation for a Japanese meetup group for Pulsar. And then they said, well, can you do the translation for it? So I said, cool. And Zoom, actually, you can also have, your language, what you call captioning. I said, awesome. So I did that when I was recording it. I said, okay, use Japanese translation too. And of course, I couldn't verify because I don't know Japanese. And then as such, when I pass it on to the organizer there, they said, wait a minute, it's all wrong. It came out, it just couldn't figure out. So I'm kind of thinking, yes, of course, because I'm talking about technical subjects, it's probably did not already have that set of data to tell it what it is. I'm talking about technical terms, it couldn't find it. So then it wrongfully looked for some kind of matching words, a nearest neighbor word, which is completely wrong. So as you can see, I think there's just still a lot of room for growth to make things more accurate. And I think it actually would be nice. I was thinking, if you travel somewhere, let's say going to Russia, I don't know Russian. So if you can have a machine that actually can immediately follow your conversation, and then it immediately can do the real-time translation for you to the Russian people over there. And I think that would be the most useful. I do see it as kind of like a very good potential kind of usage area that you can find usages everywhere. But anyway, so going back, right, I feel that there is, despite all the issues and all of these things, there's great potential of, us to continuing our job. I mean, just think of how, I think in the beginning of the Industrial Revolution, people were saying that, well, we're going to lose our job. But guess what? We still have to do jobs. There are still jobs available. So there will be new jobs. I think I'm confident we can find new jobs. One of the things, maybe we need more testing too. We need to actually test to make sure what the GPT engine is doing, are they doing the right thing, right? We need to have more control and measures over it, and that will create new jobs too. So don't worry about it, is what I'm looking at it. Okay, so a couple more issues and concerns too. Essentially too, I mentioned ethical concerns and also like potential misuse. There could be unintentional misuse too. So those are the kind of things we need to pay attention to. And as you have heard too, there are a lot of countries too. There have been, well, I guess countries, maybe cities, states already kind of banning it or stopping it from use because of all of these concerns, and we are all aware of. Okay, so then another area that I find there will be also great potential for more development is in terms of doing real-time pre-training and also like real-time inferencing. I think that's an area that that can actually leverage on what I was more used to before, which is event streaming. You can, essentially streaming, to give you a quick thing, is good for doing real-time data processing. It's capable of, ingesting huge amounts of data and do all the analysis in real time. So I kind of see it as a very good area that we can make use of streaming and kind of interdisciplinary, kind of bringing into the AI world to do this pre-training. Just think of, the fact that we have to pre-train, take so long, pre-train some model, and then you want to then do inferencing. And then you're still using stale data because there are things happening between the time you finish your pre-training and now. So that kind of real time, I think, will be the next thing that we can kind of investigate more into. And there are already things being done. For example, at DataStax too, we're doing also what we call it's actually a new product. It's called LangStream, which is kind of like LangChain, but then it's for streaming. And we're leveraging on the Pulsar. Again, the event streaming message broker, we can actually be doing like real time and then feeding in and generating that data pipeline and do data transformation as the data is being fed in. So we're kind of doing research on that, and we'll come up with this new product very soon. So just so to give you an idea. So essentially too, it's also what Tianjin talked about, the RAG pattern, right? The retrieval augmentation pattern too. And that's what can kind of leverage on that and provide us with more up-to-date data. So. Okay, so I think I might be kind of running out of time, but these are resources. But I also have a bit, like I mentioned, about an example, right? We're just talking, but there's also vector search and vector DB that DataStax gives you an opportunity to work with. So let me kind of go. Let me see. Is it doing okay? All right. Maybe I'll have to stop this one, and then let me make sure I get. I have to go back to here. Maybe. Is it? Okay, I have to share that, I think. Okay, so if you go to astra.datastax.com, and it's also in my slide deck too, I have this. Oh, it's not showing. Let me do that. Let me share this guy. Okay. Okay. Why is it taking so long? Oh, cool. So, okay, so if you go to Astra, it's our managed cloud platform. So we have our database, which is Cassandra underneath the hood. Again, Cassandra can handle NoSQL. It's NoSQL database can handle, huge amounts of data very well, and it's built for that. And if you want some example, Apple Computer is our big customer. All the Apples, they're actually using Cassandra underneath the hood. Netflix, for example, FedEx, huge companies are using it. It's great for doing big companies, big data type of thing. So anyway, we have added in the Gen AI capability, vector search into our database. So now if you want to sign up for it, you go to astra.datastax.com, and underneath here, there's sign up in the bottom. And if you sign up, you just need to give your name and then your a working email address and then your password, and that's it. We don't ask you for a credit card. You get $25 per month as a credit to use. And you can see too, if you're kind of doing personal projects, it's kind of sufficient, more than sufficient. So, okay, so let me kind of go back. Because I already have an account, I just signed in with my Google, a single sign on, and here. Maybe I'll just quickly show you. So I won't get into all the details, but just point you to it. So over here too, if you come in, and again, today's our event, I Love AI. I believe it's also being recorded too, so you can still register and watch the recording. Anyway, so if you want to try it out, do the create database, and then immediately too, you can create a regular serverless database, the normal thing, or you can create a vector database. And so, oops, let me kind of optimize for it. I picked that. Let's say I create a database called AI Camp NYC, and then key space name can be. Actually, let me do this. There's things called vector search. And then right now it's only GCP right now, I think. Although I think, well, for a feature or for vector search, I think it's GCP, but we're very soon going to add in AWS and Azure too. But for now, if you want to try, use GCP. And then the region is US East. And as you can see, the operation cost, if you click on it, right? And oops, here, oops, keep missing it. So as you can see, like read request is 36 cents for a million, right? So it should be sufficient if you're doing personal projects. So with that, you can quickly create a database, and it's very fast. It's running on the cloud, and again, use it to your heart's desire, up to $25 per month. Although, if you are, especially if you are a startup company, you want to start your company and need a database, and talk to us, because we are just so happy now, so excited. We want to share what we have, and we're going to help you with it, and also help in terms of giving you funding in your beginning journey too. So yeah, just keep that in mind. So okay, so now I create the database. Why is it taking so long? Not sure why is it taking so long. You know what? I think it could be because I already have a database. So let's say I'm create, so it's there. But if you look into here too, then I see this test database is already the vector database that I've created. So over here, you can see too, I also created one using GCP, and it's US East region too, and then key space is NYC. So over here too, you can start playing around with it, but I want to kind of quickly point out to you, since I'm already kind of over time. So if you go back to explore examples over here, so it brings you to our documentation. And over here, there are already some examples you can put your hands to trying things out, like with LangChain, quick start, like doing search, or the retrieval augmented generation, the RAG pattern for chatbots, quick start, and also image search. All of these, we have some example already there, but this one would be the simplest, I'd say, is query vector data with CQL. So CQL is basically, we give you a interaction. You can interact with our Cassandra database. So I'll quickly show you, but otherwise too, you can pretty much follow this. And I won't repeat it here because for not enough time, but otherwise too, it guides you through how can you create tables first in Cassandra with vector search, and adding in all of these attributions to make it work too. So please follow that and use that database. So, okay, so all right, then let me kind of go back, because I think the time's us up and it's getting late. So let me kind of do this one thing, go back to my slide quickly, just 1 more minute in here. It's just taking time to load. Because I'll share with you the QR code for the slide deck, so then you can get to some of the links that I was talking about too. So this is taking time. Okay, so yeah, so this is just a QR code and also the short link if you want to get a hold of this slide deck. It's here, and I'll share it with Bill too, so if you miss. And then these are just different links, and the middle one, extradatastacks.com, is the one that you can use for creating database, vector database. Use it as a playground for yourself in there, and then just a couple links for our Astra platform and streaming platform too. And then also we have a weekly podcast. I just recently joined this team. So I have actually Aaron, who's like a guru in Cassandra, and now he's guru in AI vector search. So he and I is doing this podcast. So if you want to subscribe to our YouTube channel or follow us on LinkedIn, our DataStax account too, you can get notifications when it happens too. So that's that. And then I also have a Twitch stream too, but I'm gonna start doing more AI stuff. So yeah, I promise you I will. So that's my Twitch handle. And then also some DataStax product, AI related. We have AstraDB with vector search, and also our real-time AI. We also have a company we recently acquired called Cascada. They have feature engineering too. So with that, I just want to thank you so much and appreciate your patience. And this is how you can get a hold of me, my LinkedIn. My Twitter is now X, follow me there. And also my Discord channel too, if you want to stay connected. And anything that you would like to see if DataStax can help you with your business or your project, please reach out to me or to DataStax too. So thank you very much, and thank you, Bill. Yeah, thanks. Yeah.
Do we have any questions? Maybe we can have 1 or 2 questions answered. Okay.
Sure.
The website you showed was talk about real-time data for generative AI.
Yes.
Which sounds kind of cool, but I can't quite imagine what you need it for. Can you
sure. So as I mentioned to you too, we are now experimenting. We're already developing this feature. It's going to be called LangStream. I think they already announced it, but it's actually what you call streaming for generative AI is what it is. And we're making use of Pulsar. As I mentioned, event streaming, you can build data pipelines, and there is this feature called Pulsar functions that you can quickly do, like data transformation as you are ingesting it. You can transform it really quickly in real time too. because it's an event message broker that can take in data in huge amounts too. So we're experimenting with that, and we should be having it general acceptance by the end of the year too, I believe. And so that should be good. It gives you capability to actually ingest real-time data, at least for the inferencing side right now. I think the pre-training is probably going to take time to do real-time AI, I think. Yeah, so thanks for asking. Yeah, okay. Yeah. All right.
All right. Okay. Great.
Okay. Thank you.
So much.
Thank you so much. Yeah. Okay. Thank you. Let me stop share. Yeah. Stop share and then exit. So yeah. Let me see. Stop share. Okay. And then leave. Okay. Okay. Leave. Okay. Cool. And then give it to your next speaker. Yeah.
Yes.
Thank you.
Thank you. All right. So yeah, so let's move on to our next part of the events. And before you will have a three tech talk, and the next part. Before hold on a second. Before, sorry. So yeah, just a quick update of the housekeeping things. So one is for the slides, and we're going to post to the Slack after events, so you can download the slides. We're going to share it in the Slack channel. The second one is the event. The tech talk is recorded, and we're going to later on when the recording video is available, we're going to upload to the YouTube, and you also can probably get the email notification, or we also post it to the Slack. And the slides, the recordings. Do you guys have any questions for the housekeeping part? One more thing is for the raffle. So you still can enter the raffle. We're going to do the lucky draw at the end of the event, and you can. The way to enter is just comments on the LinkedIn post, and you can do it multiple times to increase the chance. Just a tip. I'm probably going to remove the duplicate one. But anyway, so feel free to share and to post as many as you want. Okay, great. So for the next part, we're going to do 3 lightning talks. So I set a quick rule for the lightning talk. Lightning talk, each one is 15 minutes, 1-5. And please hold your questions until the very end. We're going to do the Q&A at the same, as a group after the 3 lightning talk. So we can do. All right. So let's welcome our first lightning talk speaker, Sally Ann. She comes from Arise AI, and she's going to talk about generative AI observability. Yeah, you can unmute.
All right, everyone, give me 1 second to share my slides here. All right, here we go. Hey everyone, I'm Sally Ann. I'm from Arise. I'm a machine learning solution engineer there. Thank you all for joining me tonight. I'm super excited to be here. And for today's talk, I'll be going over LLM observability. So let's dive into it. So before we get into the real content, I do want to introduce you to Arise. Arise is a machine learning observability platform, meaning we enable teams to monitor, troubleshoot, and improve models in production. And so I think it is important for us to understand what observability is. And one thing I hear all the time is people think that monitoring and observability are the same thing. But
It's actually not the case. So with monitoring, that allows you to understand when a problem has come up in production. But what the difference is observability allows you not only to identify when that issue has come up, but then actually root cause to understand the true reason behind it. So an observability platform is going to allow you to understand when those problems have come up and give you workflows and tools to help you really resolve it and make intelligent decisions to then improve your model in production. So that's observability. I want to dive into our topic today, and that's LLMs. So we've been talking to a lot of teams that are using LLMs in production, and these are really the 3 buckets of use cases that we're seeing teams put priority on. So the first is going to be assistants. These are internal tools built for internal teams to use. The second one, I'm sure everyone here is familiar with, those are chatbots. Seeing a lot of emphasis put on that as well. And then lastly, the text generative use case. So this is where teams are integrating LLMs into their existing product workflows. So these are use cases. What about our tool chain? Well, this is the emerging tool chain that we're seeing. So no surprise, LLMs is the first piece of this. And we're seeing teams use a wide variety of models. So whether they're building something in-house, leveraging an open source tool, or opting for the commercial option, we're seeing a lot of variety. The second piece is your AI memory. So that's where your proprietary data and LLM memory is going to sit. We've had a lot of talk about vector databases today, so I won't spend too much time on that, but you can see there are a few different options we're seeing different customers use. And then orchestration. So this is your LLM app framework. We've heard some people talk about Llama Index and LangChain. This is where that sits. And these tools really help you develop these applications to leverage LLMs. Last but not least, we have evaluation, and that's where LLM observability is going to sit, specifically Rise. And that's where I'm going to spend most of my time today discussing is how to handle observability. So this is our tool chain. I want to talk about this in the context of some architecture. And the good news is we've been talking about this architecture a lot tonight. This is the RAG architecture, also called search and retrieval sometimes. And so what does this architecture do? Well, we're going to start with a user query. That's when your user asks a question. We're going to then embed it and send it to our vector store. And then depending on what similarity metric you've chosen to use, we're going to retrieve the most relevant pieces of context. We'll take that context, our prompt, along with our user query, send that out to our LLM, and it will generate a response. And if we're super lucky, we'll get some user feedback back. So you can see at the bottom that tool chain we just discussed is taking part in each of the steps of this architecture. But the main thing I want to point out here is observability is going to sit across the entire stack. And there's some good reason for that. And the reason is that all these steps are happening super fast, but there's problems that can emerge at various parts in the process when you have your LLM in deployment. So first off, this was actually already touched on a little bit tonight, which is that there's no real visibility until our agents are performing. Another one is bad retrieval, so not retrieving the context that you were hoping for. Third one, bad prompts and bad prompt templates. That's a big one. Another huge one, model hallucinating. We talked about that a little bit tonight. So whenever your model is presenting something as factual when it's really not, it's a big problem, right? And last but not least, evaluation is hard. So I kind of alluded to this in the slide before. User feedback can be sparse. You can't depend on having it. So being able to actually understand how your model is performing, it can be quite difficult. But the good news is we have some observability workflows that can help you out with this. So starting over there, we can debug our embeddings. So taking a look at our embeddings, determining how well they're doing. Next up, search and retrieval troubleshooting. So again, how well is our search and retrieval process working? Prompt analysis and improvement workflows is another big one. Doing data discovery for fine tuning, that can be really, really powerful. And lastly, if we do have user feedback, we can identify those bad responses from our LLM. And so these are different problems that come up and different processes that you can use to address them. But I want to talk a little bit about how we do this. And so this is some of the data that we'll ingest and Arise to use in these workflows. We've noticed that when users are only tracking their inputs and outputs, they're having a hard time really understanding what the problem is behind their LLM, because an LLM is not giving a bad response for no reason. There's probably something larger going on. So we're going to take data from different parts of the architecture. So starting with your vector store, your knowledge base, we can take a sample of data, ingest it into Arise to understand, does our knowledge base even have the context that we need to answer these questions? Next up, we can also take your prompt and prompt templates to do that analysis, understand what prompt templates maybe aren't doing so good. Next up, understanding what context is retrieved. So a big thing when you're doing vector database similarity search, we're returning the most similar pieces of context, but the most similar is not the most relevant in some cases. So understanding that's a big one. And then of course, we'll take your response and your user feedback. That can be really helpful as well. And there's different ways you can get data into Arise. We have an SDK, we have table integrations, as well as cloud file storage. And so all this data can get into Arise. And then we can get into the good stuff. So we covered use cases, problems. Somebody here is probably thinking, well, like, how does this help me with my LLM? Well, I'll tell you how. So these are some improvement workflows that we offer at Arise. Now there's a lot of other workflows you can use. These are just 3 main ones. And so we have prompt engineering to ask better questions. We have improving context retrieval to get better responses. And then we have fine tuning to give better answers. And so I'm going to cover each of these in a little bit more detail, but these are the 3 we'll focus on. So starting with prompt engineering. So say we've ingested our prompts into Arise. We have our responses as well. So we have user feedback. And looking at this visualization here, this would be like a time series of our performance over time. And you can see there's a huge dip in performance. And what we're able to do is actually drill into that point in time and take a look at our prompts and really easily see which ones are doing well and which ones are not. And so what this allows you to do is strategically pick what prompts you're going to iterate on, do your prompt engineering, put them into production, and then you can kind of iterate on this process over and over again. And we are seeing a lot of teams get a huge positive impact in improving their model's performance simply by doing some prompt engineering. So this is a really important workflow. Next up, troubleshooting bad retrieval. So in this example here, we're comparing our query data to the context, and there's our ratio is off here. So we maybe have more queries for a specific topic than we do context. And so very similar to what we do with prompts, except we're going to drill in and take a look at our queries versus our context. And so you can see here in this example here, we have a query, lots of queries being asked about HD videos, but we don't have nearly enough context for our LM to give them an appropriate response. So what we now know is the exact topic we're missing from our knowledge base. We can go in, add those to the vector store. And so now our LLM has the data it needs to give good responses for that topic. Last but not least, fine tuning. So fine tuning costs a lot of money. I think everybody knows that, especially with these large language models. So if you're going to do fine tuning, you're going to want to make sure you're doing it strategically. And so Arise really helps you to do that. So we can take in your data, we can look at your responses, see which ones are performing well, which ones are not, and you really just identify problematic clusters or patterns in your data. What we can actually do is then find similar points to those. And now you have a data set that you can export from Arise and use in fine tuning. So you can be confident that when you're spending all this time and money on fine tuning, it's going to hopefully yield much better results because you have singled out the responses that need some work. So that was a lot of information there. And those are 3 of the main workflows. I do want to point out which path you take will really depend on your use case and what insights you find in your data. You might pick one of these, you might do a combination of these. You might start off thinking you need to add to your knowledge base and then realize that you actually need a better prompt because that knowledge does not exist in the documents that you have. So with that, I want to thank you all for joining me today and introduce you into our open source observability tool, Phoenix. So this is observability in the notebook. You can find us on GitHub. Leave us a star if you feel inclined. And we have a Slack community that's really great. We have people who are sharing work, but also bouncing ideas off each other. You, of course, have access to the Arise folks. So you can ask us questions. And that's my email there if you have any questions or want to reach out. Thanks, everybody.
Phew, that is fast. Thanks, you did a great job to control the times. All right, so let's welcome our next speaker. Okay, all right. So our next speaker is Timothy Spam. He come from Cloud Era. He's going to talk about data in motion to supercharge AI. Let's welcome Timothy.
A handheld lapel mic is great. So I'm going to try to do this even faster than her. Get through the slides quickly. They're all available. And then I'll show you as much demo as I can on 3 different platforms of models, 3 different type of models, how you can get data to them and classify things really quickly and easily with full lineage and provenance. And we'll show you some cool stuff. I do meetups in the area and lots of cool stuff. You need a lot of different things, as you saw before with starting at the beginning with this stack. So this isn't even including the full stack just to build up all those different models, but there's a lot of tools out there. What's great is most of them are open source at this point, which is awesome. The parts I'm going to focus on today are how do you get data in? How do you get to the model? Once you have it deployed and running, how are you going to use it? Now, certainly, yeah, there's a prompt, but I could tell you that's not going to be every application. There's times when you need that automated. Like say I want to pass through every article I've ever written on Medium. How can I automate that? Am I going to type all those in? Am I going to write code to do that? I don't want to write code to do simple things like read the entire Wikipedia or download a database from any kind of company. So we make that as easy and automated as possible. So ingest all the things before you can augment your data, before you can do training, get everything in, Spark, all that kind of fun stuff. Then we enrich it while it's going through so we can get rid of some of those stupid things that the LLM will do, like tell me the weather and it's completely wrong. Tell me addresses that are nonsense. If I have them stored already, why am I not using them? If I know what's absolutely true, use that and let LLM fill in the bits that we don't know or we don't know yet, or how to tie them together. I've got a couple of these. These are all in GitHub. One's against a Bloom model. One's against a Distilbert for sentiment analysis. I've got another one doing Google, Flan, T5, XXL. Rolls off the tongue, these model names. Whoever names these is not cool. They don't have cats. I've got stickers over there if you want some later. Also, you've got all this model, you got all this cool stuff done. Where does it go? You're gonna just run it on an expensive place. We could deploy, and I've deployed it out to little Jetsons on the edge, move those automated. That's a pain. Store stuff, certainly store stuff in my friend Milvis over there, which is awesome. That's our default vector store. But you got to store stuff a lot of places, like, I don't know where Mary is, Cassandra, lots of different things, because not everyone wants their data in the same place. It'd be nice if they did, but they don't. If you want my slides, they'll be posted, but there's a cat in there. That's QR code. Another part I'm going to show you is how we're using LLM plus a knowledge base and have that deployed in your own infrastructure without having to rely on OpenAI. And I'll show you a very quick part of that because we got only a couple minutes. So we take an open source LLM, one of the ones from H2O, put a little enterprise app on top of that with full security, use a Milvis vector database in there, and then connect it to actual data from enterprise data stores. We're doing this for a couple banks already. So taking an LLM and combining it with an existing 20, 30 petabyte data store is a nice combination of stuff. I run some meetups and other things. No more clicky. So I am not a web designer, so this is ugly, but it works. So I heard there was people in the audience who know how to make web pages. This in GitHub, make a better one. But what this does is send my prompt through Magic Space to my laptop, which is running everything in this demo. Send it there to a live stream. The live stream cleans up the data, enriches it, sends it to a bunch of different models, one hosted on IBM's Watson X, one in Hugging Face, another in Cloudera Machine Learning, and then gets the results back. And then I put them in a dashboard at the bottom. Dashboard in the bottom is powered by real-time analytics. So to make this as simple as possible, there's only 50,000 things on the screen. What's interesting is what you're seeing on the screen is not a diagram. This is the live code. This is how you write the code. It's drag and drop, little boxes, connect them. It's kind of fun. This is a web server I wrote in this open source tool, Apache NiFi, that's handling those calls from that web page and also hosting that web page and dynamically getting the data back. And then it sends it into a call to the Blue model hosted on Hugging Face. But this could be any model you've deployed. But LLM models obviously are talk of the day, but doesn't matter to me other than it may cost more. It may take longer. So one thing you might want to know when you make those calls is attributes about them. And what's cool about this tool, NiFi, is it grabs all the metadata. So I know everything that happened, how long it took, what it did, what was the size, every bit of audit data you could possibly want. As a disclaimer, this tool is open source out of the NSA. They use this to track live missile systems. So it is pretty reliable, because if it wasn't, there you'd be seeing the wrong things blow up. So, but we're using it for good here, moving models around, getting pictures of cats, all kind of fun stuff. What's cool with this tool as well, I could drop in real SQL and use that to convert and change things. You know, I could take XML, convert it into JSON, convert it into other formats. I have data coming in from travel advisories, that's RSS feeds, all the weather in the United States, live MTA feeds, live camera feeds. I could do images, text, structured, unstructured, same tool, real time. So that comes through. At the end, I push it into Kafka. I could push it to Pulsar, but Mary's not here, so she won't get a call out. And then I put it into a live SQL engine that can combine that data with different model results. Also do lookups from other data stores, do that real time. And then at the end of it, create a materialized view. A materialized view is a REST endpoint that returns JSON. And everyone knows what you could do with REST endpoint with JSON. Pull it into a Jupyter notebook, pull it into an application here. This is just using a jQuery data table to read that, that REST endpoint and display it here. And I can also interact with lots of other systems for output, including say Slack, Discord. So I could take the results out of what I was doing and put it here. For tracking me running stuff, I could also put how much it costs. So when anyone's running a model at your job, you could go, hey, you're spending a lot of time doing this. You should use Milvis's GPT cache. You're not running that thing again. Give you a shout out to my buddy there. Then the last part I wanted to show you is Cloudera's app, which you could see we had someone who knows how to design apps do that for us. And what it's doing is doing a generic call with no data augmentation. And then the second one, it's reading our data that's stored in Cloudera data store, but it could be stored in any open source data store. And as you can see, with no contextual database, it's still pretty good. The questions that people run all the time probably come out a little better, but under the covers, we deploy a whole lot. And I put the link in here so you can see all the stuff that's running here. We deploy the whole model, deploy the vector database, train all that, connect it to the data stores. Pretty easy to do for us, but just to give you an idea of some of the stuff we could do. If you're curious and you want to try this out, I made the hardest to read, but I thought it was cool background, which does track. I mean, what are you gonna do? But you can download all this for free and run it in Docker. And it's really hard to read because I put a cool background in here. Because I want to see how many cool backgrounds I can put in stuff. Which maybe I should run this to out through a model that pulls these out. I could actually have NiFi do that because NiFi could read PowerPoint. And it could, I've done that, pull it out, take all the text out, and then convert it to another language. I did that when I did a talk in Montreal. Now, I don't know if it was right. Remember the Japanese language problem? I don't speak French. No one threw anything, so it's probably right. Or close enough, or people didn't care. All those are possible. I think I've finished in under time. I know people want to get out of here. I think we're all doing questions as a group to save time because we've got one more talk, right?
Yeah.
Okay. Thank you.
That's the leave. Great job. Control times. Thank you so much. And great, of course, great presentations. So yeah, hold your questions, and we're going to go through the last lightning talk, and then we'll do the Q&A together. Our next speaker, Andrew, he come from Last Mile AI, and he's going to talk about developer applications on generative AI technologies. So let's welcome Andrew.
I'm not going to attach. I'm just old. Cool. Hi, everyone. I'm Andrew. I am the co-founder and CPO of Last Mile AI. And Last Mile AI is a tooling suite for foundation models. So a relatively new company. We worked together at Facebook. We actually left all together to build this generative AI platform. I'm the person who've actually been at all three of these companies working on ML platforms. And when generative AI took off, it was like kind of a light bulb for a lot of us, where a lot of the ML tools that have existed don't really fit the paradigm and the pattern for generative AI. And so what does it actually look like to build something that's catered towards this new era of ML? And so we went on to solve the last mile problem. What is the last mile problem? Well, from a foundation model, let's say ChatGPT, GPT-4, or Claude 2, how do you actually put that into production? It's kind of difficult. So you have the endpoint, you have an API, and then you have to do some prompt engineering. Let's say the prompt engineering is going, but the answers aren't good enough. And so now you're trying to figure out, how do I add my own data in? Is that through data preparation and adding in additional context? Do I fine tune the model afterwards? How do I prevent certain hallucinations? How do I put the right safeguards into place? And so at Last Mile, essentially we want to solve this problem, which is with the foundation model, people are a lot closer to getting a lot of business impact from these models, but there's still this last mile of work that needs to be done. And so we're laser focused on solving this. Most of what I want to show you is actually demos. It's really boring to look at slides, and so I just want to go through as many demos as possible. One slide maybe I do want to show, I think people might be interested, is just a high level diagram of usually what happens when people try to go end to end with these generative AI models. You start from your prompt engineering, and then you go into something called parameter tuning. In traditional ML, it's called hyperparameter tuning. This is like the number of epoch, the learning rate. Afterwards, you do either an ad hoc evaluation, which is kind of a spot checking. You look at it and say, are the answers right or wrong? Or you do an offline evaluation, which is, I have a lot of data and I just want to feed it through to see what are the results. Is it accurate or is it inaccurate? Afterwards, you prepare your data. You do something called grounding or memory augmentation, or you do your fine tuning. You deploy the model, you integrate it. You set up some type of rule-based engine afterwards, or caching or audit logs. And then you can either do human in the loop style, where people manually label things and feed it back into the model, or you can actually set up the rules and prevent certain types of behaviors and feed that back into the training of the model. Just a quick diagram just to showcase what the last mile problem is. But I'm just going to dive into demos if that's okay with folks. So this is the Last Mile AI workshop. It's basically the place that I use, part of our product for using generative AI, we want to make it as simple as possible to use generative AI. We've worked in AI for about 6 years, 7 years, and it's always had a lot of friction to use. You know, it takes a lot of effort to actually clean all your data, create your features. And so how do we make it as easy as possible? So the first step for our startup is building this kind of workbook-esque system. And so I don't know how many people are familiar with like Jupyter notebooks, but essentially we've created our own right here where this first example is, I don't know, how many people have used Stable Diffusion? A few hands. It's really hard to get the right prompt. I don't know how many people have been able to generate a good prompt for Stable Diffusion. It's extremely difficult. There's many limbs that appear. It is haunting. And so the first thing that we did was we basically wrote out a prompt where to GPT-4 generate us the system, the actual prompt for Stable Diffusion, because I can't actually write it in the perfect way, but GPT-4 is actually quite good at it. And so we have this system prompt here. It's quite long. We feed it with some examples so it understands the general structure. And then we can basically say, I want a planet far away filled with vegetation. So I can execute on the fly. And right now it is creating the prompt that I want to feed into my Stable Diffusion 1.5. And so from here, I can actually reference it through this variable, and I could generate it through Stable Diffusion 1.5, and I'll render about 4 images for this type of example. Stable Diffusion does take a little bit longer, but you can see here 4 examples. This is pretty cool, but let's make it a little bit cooler. What can we do next? I can actually now start editing this, right? So I can tell GPT-4 again, assume that you're a really good artist, and I'm going to give you the prompt. I want you to change it with another variable. And so I set this variable as I want this to be, let's make it aquatic. So I set the parameter, I execute it again, and now it's generating me a new prompt that's going to be more aquatic focused. This is great. So now I have a new prompt that I can feed back into Stable Diffusion. And Stable Diffusion will now output more aquatic-based systems based off of the same prompt as the original one. I'm just using GPT-4 to chain it so that it could generate new results. This is one example. Something that's a little bit more concrete for folks that are working with businesses, translation. I know translation has cut a few times. And so we're working with a few folks on translation. And so for this one, what we've done is we have some sample text. I actually took Azure OpenAI's text, and then I said, I want to translate this to Spanish. And so I have a parameter here, which is the target language. I set that to Spanish. A few things I've done with prompt engineering here that's pretty useful. One is within Spanish, there's a formal tone and informal tone. I can actually specify into the model to make sure the tone is proper. I also have an exception list. There's a lot of words that shouldn't be translated. It means something specific. So Azure is a specific term that Microsoft uses. So I don't want that to be translated. So is generative AI and AI in general. So I actually add an exception list. And so now I could actually generate the translations here. And it's going to generate the translations based off some of the rules that I set up with my prompt. I don't really speak Spanish that well. There might be a few folks who speak Spanish really well here. What is one of the most common ways as of today to evaluate whether the model does it right or wrong? As funny as it sounds, the leading way right now for people on how they think about evaluating is actually feeding it back into GPT-4. So you give it back into GPT-4 and say, here's the original text, here's the translated text, please grade it on a certain scale. So I have a new prompt over here that says, here's the original text. I feed in the variable for the translated text, and I say, please give it a grade between poor, average, good, and excellent. And here you can say it's pretty good. And so this is an example of how you can kind of set up evaluators. But yeah, these are just a few of the demos. There's also audio models if people are interested, which is from your voice to actually get in the actual text. We're exploring a lot of ideas of, as you have a lot of meetings, it's really tiresome to write up notes, automatically record it, and you can actually structure it, diacrize it. So whoever's speaking is labeled as that individual, summarize it, and send it out. Really cool technology. We love giving kind of a free-form playground for people to use. And from here, it actually gets productionized where you can actually put it into production. We want to make it dead easy so that people can use this as much as possible. So yeah, so let me go back to the slides. That's about it. This is our QR code if people are interested. I use ControlNet. So ControlNet actually can merge multiple images together. And so I've just put in our QR code with the Empire State Building. We're working out of there now. And so I was able to kind of generate that in. And yeah, check us out. Feel free to connect with me. I love talking. And so I would love to connect with everybody. But yeah, we're really excited about this technology. It is truly revolutionary, and we want to make sure that it's easily accessible to as many people as possible. Thank you.
All right, that's great. Thanks. Let's do a Q&A time. Yeah, you can just exit.
Okay.
Yeah. Stop share. Yeah, stop share and leave the meeting. Yeah. Okay, great. Yeah. So yeah, we can just start in the Q&A time, and we have that 3 speakers. John. Yeah, so if you have questions, you can specifically to which speaker and raise your hand, and I will pass the mic to the speaker to answer. Oh, sorry. Try to get out of the way, and anybody has question? Go ahead. Sorry, what? I mean, sorry. Yeah, you can just. Is the question for
yeah, I'm just trying to figure out. This is just very general. What is AI doing to promote human connection?
What's AI? So, is anyone, any other speaker you want to take it? Okay.
AI is forming these events together so that we can all sit and talk to each other. Otherwise, we just sit and you webinar.
I do think it's fair to say that I think AI gets a bad rap as if we're going to take over the world. And I think, Mary, you mentioned that the jobs are going to be taken over, but you have to look at the applications that AI is making a difference. I mean, there's work on implementing AI so that people can communicate, through sign language or through different languages, as your example. There is ways that AI is going to bring people together outside of just creating these amazing events where we all get together and talk about this stuff. But while we might be talking a little bit about business applications today, there are a lot of people who are thinking about societal problems and applying AI to it. So I do think it's
one of the things about how does this engage adults with children? I mean, they're the ones who are going to
they are applying AI in schools. Whether that's the best application for it or not, I can't really speak on how it's doing that specifically, but every aspect of human life, people are looking at the equation and thinking how we can apply AI to it and how we can make society better with AI. I think everybody in this room has the belief that AI can make things better. And people are looking at all different angles and how we can apply it. So that would be my answer to that question. Yeah, go ahead.
One of our individuals on our team had a child, and hello, yes. So one of the team members on our team has a child, or has a friend who has a child, and one of the things that he was looking for was every night he reads her a bedtime story. And in that bedtime story, it's really nice when you can actually incorporate the child back into the story. And with AI, basically that was all feasible, where right now there is like a workbook that they use every night. They generate a story, different area, different plot, different landscape, and they incorporate the children into it so that there's always a new bedtime story. And I think it's AI is facilitating different things and starting to really make things a bit more personal. And so there's a lot of new opportunity, and we're pretty excited about it. Yeah.
Great. Speaking about the storytelling, the bedtimes, and Eugene, do you remember last weekend we have the AI hackathon in Seattle? Yeah. And one of project is exactly like that. Personalize your storyteller, and based on your, the kids. I think one of the story they generated is the kids don't like a carrot, and they. And then they generate a story, and the kids don't like eating the carrot, and the parents struggle with that, and then they generate that story and read it to the kids, and that kids seems like start to eat a carrot. Very fascinating project. Actually, it come from our AI hackathon last weekend in Seattle. All right, any other questions? That's great. All right.
So, Sally-Ann, you were saying that if you want to use large language models with like your own company documents, whatever, then you can fine tune the model on those documents. Earlier, Jan was saying you can use retrieval augmented generation instead. So when do you do fine tuning? When do you do retrieval augmented generation?
So I think my answer to that would be really like, it depends. I think it depends on your use case. Sometimes if you're using, like if you're doing search and retrieval, I personally would opt to do that before I try to fine tune because it's going to cost you a lot less money. So my personal experience has been iterate on your prompt, change the way you're doing your retrieval. And if all of that doesn't work and you still need your model to do something super specific, then you might start thinking about fine tuning. So that's kind of the approach I take.
Yes. So from what I've seen, in my experience, and this is also recommended by OpenAI and also Porsche, is fine tuning is really good for style transfer. So if you want to have your model say things in a certain way, fine tuning is good for that. It's not very good for factual information. And the reason for this is, I mean, it's pretty intuitive if you think about it. How much data is ChatGPT trained on? And how much data do you have to train ChatGPT on? And so that's why you would use RAG for factual information stuff, and you would use fine tuning for style transfer.
Yeah.
You can just hold it. I have this one. Any other questions? Okay, maybe you can just speak loud.
Yeah, so is your question, sorry, it was a little hard to hear you from all the way over there. So is your question what our plans are for the future for like LLM monitoring, observability, and evaluation? Yeah, so we have a model ops. Okay, so our focus is always going to be observability. So really understanding root causing issues. So right now, our focus is a lot on LLMs. So you'll see continued support for the workflows that I showed you today, but even more like ranking metrics, for example, for finding relevant context. And just more and more stuff related to evaluating LLMs. I can share with you our roadmap. That'd probably be a better way to go down the list of all the things that we share. I'll come find you after that, I can share that. But yeah, we're just putting a lot of focus on really understanding why these models are making the decisions that they are, or why LLMs are making the responses that they are. And so that's our emphasis. And as we work with teams that are putting out these very powerful models in production, we're learning a lot and we're taking that and implementing it. So I thank you for the kind words about the work we're doing, and just stay tuned because we've got a lot to come.
Any other questions? Okay, on the side. Maybe you can just speak up.
Yeah, sure.
Okay.
I'm wondering about any regulatory agencies or ops that are present in quality control and also primary technical data and so on and so forth. Are there any new forthcoming developments in that space?
Do you have an answer? I have to, yeah.
So that is definitely a big problem that we're facing here in the US, and Europe is actually much more advanced on that than we are. I will say I have run into a company recently that is doing something that is basically like ensuring where your data is coming from. And they're using blockchain with AI, so that's always fun. And it's called Origin Trail, and they're building a decentralized knowledge graph that allows you to see where data is coming from.
Team or Andrew, if you have something to add on, feel free to.
Oregon Trail is a great game.
Not Oregon Trail, Origin Trail.
I know. I'm saying that must be someone with some long experience with computing, which is really awesome.
Nobody died of dysentery in Oregon Trail.
You don't know yet.
Yes, not yet,
Come
not
on,
yet,
you
not
don't
yet.
trust LLM, says you don't need to drink water anymore, you know.
That's true, that's true.
Don't listen to everything LLMs tell you. Always fact check. Oh.
Or you can just speak up if you. I'm
So, like, do you have like AI plagiarism checkers as well? Are there ways we can like fine tune our models so that we can kind of bypass those techniques?
That's a good question. I'll give you my take on that. So what I know about these fact checkers is it's really looking at the patterns in which these models will predict answers. So they're identifying those patterns. So I kind of assume there's probably a way around it, but I think it would just be making sure you kind of have your model predict in an unpredictable way.
Yeah, my answer to that is just don't plagiarize.
Yeah.
Sure. Yeah, cite ChatGPT. Then you got to get ChatGPT to cite what they're doing there. Yeah. There are LLMs to cite now, though.
That to say you're using it. So there's really no shame in just saying that, like, hey, I had ChatGPT proofread this for me.
Okay, so let's take okay, one more question over there.
Yep. Yeah, so the user feedback is really interesting. It depends a little bit about your application and your use case. So all the things you mentioned, having like a third party do it for you, having an internal team do it for you. You also, if you use ChatGPT, you'll notice they have a little thumbs up, thumbs down on the responses. That's user feedback too. So it just depends on kind of how you have it set up. Again, I don't know how many times anybody here, I've never personally thumbs up or thumbs down a response on ChatGPT, which goes to my point, it's a little bit hard to come by. So what we're doing is, it doesn't matter where that's coming from. We would just take that and ingest it and basically use it to add context to the different embeddings that we're ingesting throughout the process. Does that answer your question?
Yeah, I was wondering that thing. So I was like, actually.
Yeah, it's a problem. I always think twice. I feel like I should, because I deal with, other, customers who have that same issue. Like, user feedback is really sparse. Like, not a lot of people have it. That's why we need all these other workflows to understand how the model is performing, because odds are you have very little user feedback to identify good and bad responses. Yeah, forcing users to give feedback, I think, is a bit of a tricky problem at hand. We're thinking about how maybe we could tie that into the platform, perhaps allowing to do that kind of feedback inside Arise. So if you are doing your analysis and you see a problem that's like clearly wrong, you could quickly mark it as such. But yeah, it's a problem that we're definitely thinking about, because it makes things really difficult when you're users. And I can speak from experience because I never provide feedback.
Okay.
On the
Yeah,
front
the last question.
on the front end, when you're ingesting data to put into a vector database, and I saw these slides, you put an element, it's very general. How do you decide which one to use? Depending upon the space of the data you're in. Yeah, in marketing, I do one thing, I'm in legal, I do another. How do you decide which one to use? There's one size fits all.
Yeah, are you talking about the tool chain that I showed where it had the LLM, yeah. I'm just going to clarify what I was showing on the toolchain, and then yes, he is definitely better to answer this question. But that was just like a general flow of how the tools. There's no need to put like one before the other.
Right. So you don't necessarily need to use an LLM to put things into a vector database. What you need is you need to vectorize the data, and you need an embeddings model for that. And the reason why people typically put LLMs there right now is because OpenAI has a very popular embeddings model, and people will use that a lot. What you want, let's say if you are in marketing, or if you are in sales, or if you're working with CSV data, or if you're working with paragraph data, you're going to want models that are trained on the type of data that you are working with, so that the latent space created by the vectors from the model correspond to the latent space that you need in order to form the responses specific to that vertical. It can be both, right? Because there's many different types of text data. For example, you have chat data, you have data that shows like speaker 1, speaker 2, speaker 3. And then you also have data that comes in paragraphs. And then you have data that comes in a CSV. And you have data that comes in a PDF. And you have data that comes in, very weird kind of structures. And maybe it's just notes. And so depending on what your data looks like, you're going to want a different embeddings model for each data so that you get the best performance. No. Actually, I'm publishing a blog about this. I'm writing the blog. I've been writing the blog for like a week and a half or like 2 weeks now, but I've been traveling, giving talks, so I haven't been able to finish it yet. But I promise it's coming, and there will be a resource for you for that soon. I'll post it on LinkedIn at some point. It's not finished yet. It's like literally it's a draft. I'm actually writing the sections like I was doing that earlier. That's literally what I was doing after my talk.
All right, thank you so much. I think we have run out of times, and let's give all of